Mm, tengo que cambiar el layout del... No importa. Déjame que pongo un segundo. Bueno, estoy con esto. Bueno, estas son las dos secuencias de Fibonacci, una con función normal, la otra con una función recursiva. Entiendo el concepto, pero no es algo que, bueno, que todavía lo comprendí del todo. Si bien esto lo estoy haciendo con ChatGPT, o sea, entiendo cómo funciona. Bueno, esto es lo que hicimos. Después, bueno, dice para poder ejecutar la función, o sea, podemos hacer con un npm, escribiendo un archivito JavaScript y ejecutándolo con un npm. Bueno, un video de Kanakami Stepping through Recursos Information. Ok, vamos a ver este video y espera, vamos a poner pausa a esto. Vamos a ir para acá. Ok, vamos a poner.
Recursive Fibonacci function. So I'm going to assume that someone calls the function with an argument. So they call Fibonacci of, and they give pass 5 as an argument. I don't want to pick too large of a number for the argument, because otherwise I'll be explaining this forever. So let's try Fibonacci 5. So in this situation, within the context of this function, the parameter n right here is going to be equal to 5. So in that first pass, the parameter n is going to be equal to 5. And the way we wrote it, we said if n is less than 2, return n. Well, 5 is definitely not less than 2, so we're going to go to the else part of the if clause, or the else clause. And we say return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So when I call this, it's essentially going to be reduced, if you want to think of it that way, or simplified, or I guess it would return. This thing is going to be the same thing as Fibonacci of, remember, n was 5, so n minus 1 is 4,
4
plus
más
Fibonacci,
3.
Fibonacci of n minus 2. Well, in this, when we ran the function here, n was 5, so 5 minus 2 is 3. Well, these are just more function calls. So now we're going to go again. But now n is not 5, it's now 4 and 3. So let's try this out. So over here, n is equal to 4.
4.
N is equal to 4. So
4
once again,
menos
4
3.
is not less than 2. So we don't do this
Menos
part. We
1,
go to the
3.
else. So we're going to return
4.
Fibonacci of 4 minus 1, which is
Ok.
3. So this is going to simplify to, or Fibonacci, or break down, I should say. Fibonacci of 4 minus 1, which is 3, plus Fibonacci of 4 minus 2, which is Fibonacci of Fibonacci of 2. So this right over here will essentially return this. And this over here on the right, Fibonacci of 3, let me draw Let me make it because it's going to get jumbled up soon. So this returns the stuff in magenta, and then the stuff I underlined in green will return. N is now 3. 3 is not less than 2, so you go here. Fibonacci of 3 minus 1, which is
Pause.
Fibonacci of 3 minus 1, which is Fibonacci 3 minus 1 of 2, and plus Fibonacci of 3 minus 2, which is Fibonacci of 1. And then we're going to go over here, and we're going to have to calculate each of these things, because these are just more calls to Fibonacci. And Fibonacci of 3, so you can see how this is getting pretty involved right now. In fact, I'm going to start writing fib, short for Fibonacci, so I don't run out of real estate. Fibonacci of 3, when you call it, n, 3 is not less than 2, so you're going to go here. That reduces to Fibonacci of 3 minus 2. So that is Fibonacci, I'll just write fib, short for Fibonacci. Fibonacci of 2 plus Fibonacci of 3 minus 2 plus Fibonacci of 1. So it reduces to that, or breaks down into that. And then over here, Fibonacci of 2, 2 is not less than 2, so we're going to have to return Fibonacci of 2 minus 1. So that's Fibonacci of 1 plus Fibonacci of 2 minus 2. So plus Fibonacci of 0. So it breaks down into those two calls to Fibonacci. And then over here, Fibonacci of 2, same thing. We made a call to Fibonacci of 2. That's going to break down just like this call to Fibonacci of 2 did. It will break down to a call of to Fibonacci of 1 plus Fibonacci of 0. So we get that. And then we have Fibonacci of 1. This is interesting, because when n is equal to 1, now all of a sudden this clause up here becomes relevant. Because now n is less than 2, and it says return n. So this right here is going to simplify. This term right over here is going to simplify to 1. It's going to evaluate to 1. And then we look at all of these over here. Fibonacci of 2, we know that Fibonacci of 2 evaluates to Fibonacci of 1 plus Fibonacci of 0. So let me write that over here. So this over here is Fibonacci of 1 plus Fibonacci of 0. Fib is short for Fibonacci. And then we know Fibonacci of 1. 1 is less than 2. N is 1 here, so we're going to just return n. So this is going to return 1. Fibonacci of 1 just returns 1. Fibonacci of 0, well, 0 is less than 2, returns 0. Fibonacci of 0 returns 0. Fibonacci of 1, we've seen it, it returns 1. Fibonacci of 0 returns 0. And then Fibonacci of 1 returns 1. Fibonacci of 0 returns 0. So the whole time that the interpreter is processing this recursive function call, right over here, it kind of has to remember all of the previous, how it got there. Because once it eventually gets down to the base cases, it gets down to n equals 1 or 0, and actually gets a numeric response, it then has to build up to its previous response. So Fibonacci of 2 right over here, it's 1 plus 0. So Fibonacci of 2 is going to simplify to 1. This Fibonacci of 3 was going to be Fibonacci of 2 plus Fibonacci of 1. Those had simplified to 1, so this is going to be 1 plus 1. This is going to be 2. We go over here, Fibonacci of 2. Fibonacci 1 plus Fibonacci 0, 1 plus 0. This is going to be 1. Fibonacci of 2, 1 plus 0. This is going to be 1. Fibonacci of 1, well, that's just 1. And now we go up to this level. We're kind of reconstructing it back so that we get to the original function call. And I'm not going to go into the details of how does the interpreter actually doing that. This is actually a fascinating discussion. But I'll just think about how do we think about it, what's happening in this recursive function call, and why is it working? Why is it giving us the right answer? And then we go over here, Fibonacci of 4. Well, Fibonacci of 4 is the fourth Fibonacci term is the sum of the third and the second Fibonacci term, which we've already figured out. Those are 2 and 1. You take their sum, you get 3. The third Fibonacci term, by the definition of the Fibonacci sequence, is the sum of the first and the second terms. The first and the second terms, those are each 1. 1 plus 1 is 2. The fifth term, the fifth Fibonacci number, the fifth term in the Fibonacci sequence is the sum of the fourth and the third terms. Those are 3 and 2. 3 plus 2 is 5. So this thing right over here is going to evaluate to 5. So hopefully that clarifies a little bit of how this recursive program is actually working. What's neat about it is it wouldn't work if you didn't define the base cases, the Fibonacci of 1 or Fibonacci of 0. Then it would just keep calling itself forever and never get anywhere. What the key with recursion is it can call itself as long as every time you call itself, it's making its way down to the base cases. So at some point, if it keeps calling itself, keeps calling itself, eventually it's going to able to build back those calls as or it's able to get to the base case and then reconstruct what the original value is from that. And so that's why this is working. Every call to Fibonacci is a simpler version. I have a lower n, and eventually my n's are going to get to the base case, which will actually give me actual values that I can then reconstruct for our original call. So hopefully that helps a little bit. Recursion can be confusing, but at the same time it's kind of elegant and beautiful in its own way.
Horrible recursión. Okay. Perfecto, Merchos. Sorting algoritmos. Can be strange or right here.
Yeah, I've been running and running to keep it 100. It's all that I wanted, but lately I don't get the stomach. The higher the summit, the harder the plummet. They know me all over this planet. I'm just a man and I can't understand it. Proud that I win and I did it myself. Probably wouldn't if I got the help. Hearing subliminals all on myself. Feel like I'm breaking, I'm falling to hell. Told me I'm sick and I tell her, oh well. Rather be dead than to know that I failed. Live for the chase, life is a race. I'm out of space, I'ma get on my face. I got a taste, want the whole plate. Finna get laced if you step out of place. Like, first off, you don't run nothing. All talking, your team bluffing. My squad, we all dream crushing. We ain't rushing, no discussion. All I know is us made for this. Paid for this, yeah, slave for this. Been down and I'ma get it right. Get on sight like. Been down and I'ma get it right. Get on sight like. Been down and I'ma get it right. Get on sight like. Never really know when you're gonna go. Why you gotta put another foot in front of yours? Bury them toes, carry them close. I was never one to care about my mentos. I was like froze, now I'm on floor. Give me that smoke, but I can't get high. We do the most, here to inspire. Doing what I'm supposed, but I can't get tired. Run for your life, every night. See in the dark, blind by the dream crush it, we ain't rush it, no discussion. All I know is I was made for this, paid for this, yeah, slave for this. Been down and I'ma get it right, dead on sight like. First off, you don't.
Okay.
All right, so by now we've talked about a couple of different sorting algorithms that are pretty straightforward to work with, hopefully. We've got bubble sort, insertion sort, and selection sort. And what we do know is that all of them have in common is that they have a sort of worst case scenario runtime of n squared. Can we do any better than that? Well, the answer happens to be yes, we can, using an algorithm called merge sort. Now in merge sort, the idea is to sort smaller arrays and then combine those arrays together, or merge them, is the name of the algorithm itself, in sorted order. So instead of having to think about we have one 6-element array, let's think instead that we have 6 1-element arrays, and then let's just recombine them in the correct order and merge them together. That would be one way to sort it, and that's what merge sort does. And it leverages something called recursion, which we've talked about which we'll talk about soon in another video. And if you want to get a better understanding of how recursion works, you might want to take a look at that video before coming and watching this one, because this is going to talk about recursion quite a bit. Merge sort is definitely the most complicated of the 4 different types of sorts that we cover in the class, and so I'm going to go through this one a little more slowly than the other ones. But the algorithm for merge sort itself is actually pretty few steps. We're basically going to say we're going to sort the left half of the array, sort the right half of the array, and then merge the 2 halves together. That is fundamentally what merge sort is all about. Of course, in practice, it's a little more detailed than that, but let's go through it now. So here's the same 6-element array we've been sorting all the time. And we're going to start to follow our steps of pseudocode, which is we want to sort the left half of this brick red array. So we're just going to focus on this part for now. And actually, just to make things a little bit easier, and because I've colored different things in different ways throughout this video, we're going to refer to this half of the array, this left half of the overall red array. From this point forward, this is the purple half of the array. All right? So we are now in the middle of sorting the left half of the array, but we don't know how to do that. We don't know how to sort the left half of the array. So why don't we just go back to our merge sort steps again? All right, well, if I don't know how to sort the left half of the array, I'm just going to start again. Sort the left half of this array. So now I just want to focus on this part of the array, the left half. And I'm sort of arbitrarily deciding that my left half is going to be smaller than my right half. I have 3 elements. I can't divide it evenly. I can't have 1.5 elements on each side. So as long as I'm consistent, as long as I always choose, in this case, the left side is smaller, that'll be fine for merge sort's purposes. So now I'm left with this single element, this 5. How do I sort a 1-element array? Well, the good news here is I actually don't have to sort it at all. A single element array must necessarily be sorted. So I can say that if I'm sorting the left half of the purple part, that is sorted. So we're just going to call that sorted and set it aside for now. So now I want to go back to the right half of the purple part. That's this. How do I sort this array, this subarray? Let's just go back to our steps again. I want to sort the left half only. The left half is now 2. It's a single element. I know how to sort a single element. So I've sorted the left half of this, the left half of the right half of the purple. That's where we are. That's sorted. Now I go back and I sort the right half of the left half of the purple, which is the 1. 1 is a single element. It's really easy to sort. It's in sorted position. Now is the first time I finally get to this 3rd step of merge sort, where I merge the 2 halves together. So here what I have to do is consider these 2 light green halves. And I have to decide which one has the lower element. In this case, it's 1. So what I do is I take the 1 and I put it in the first position of some new hypothetical array. Then I compare the 2 against nothing, and I ask which one is lower. Well, 2 or nothing, what's lower is 2. So now let's reframe the picture, because remember we're talking about recursion. We're only focusing on the left half of the overall brick red array, which we then called the purple array. By this point in our steps, with respect to the purple array, we have sorted the left half, which is 5, and the right half, which is originally 2 and 1, but now we have done these merging steps and we've got that in the correct order. So now we are on step 3 for the entire purple array, because we've already sorted the purple array's left half and the purple array's right half. So now we need to merge these two halves together. And just like we did a second ago with the 2 and the 1, we're going to compare the first element of the left part and the first element of the right part and figure out which one is smaller and make that the first element of our new array. So I compare 5 and 1, and I say which one is smaller? Well, it's 1. So 1 becomes the first element of this new 3-element array. Now I have to make another decision. Is 5 lower or is 2 lower? Well, 2 is lower, so 2 becomes the next element of our merging step. Then I say, is 5 lower or is nothing lower? Well, clearly in this case, the only option I have left is 5. And so now, at this point in the process, let's again think recursively about where we are. We have sorted for the entire red array. We have just done step 1. We have sorted the left portion. We've done so recursively, but we have sorted the left portion of the overall red array. So we can kind of put this aside for now, because now we have to go to the next step of the merge sort process, which is to sort the right half of that red array. So let's go over and focus on the right half. We're going to go through exactly the same steps that we just went through with the left part, but now we're going to do it with this red part on the right. So I want to sort the left half of this array. Well, that's pretty easy. I just arbitrarily, again, divide it. I look at it. I say, OK, well, 3 is a single element. Single element is already sorted, so I don't have to do anything, which is great. I can just set that one aside and say 3 is already sorted. Now I want to sort the right half of the not so brick red, but is still red, half of the array, which is this section. How do I do this? Well, it's more than one element, so I'm going to go back to the beginning of my process again. I'm going to sort the left half of that array. So I look and I say, here's the left half. It's 6. It's already sorted. Now I'm going to sort the right half of the array. It's 4. It's already sorted. Now I get to that merge step again, where I have to, again, do these sort of side-by-side comparisons. Which one is lower? Is 6 lower or is 4 lower? Well, 4 is lower, so that becomes the first element of our new merged little subarray here. And then I have to choose between 6 and nothing, and I say 6 is the lowest remaining. So now I've sorted the left half of the right half, and I've sorted the right half of the right half. So now I want to merge those two portions together. And again, we're going to do exactly the same process that we did for the left portion. I'm going to say, is 3 lower or is 4? Well, it's 3. And then I'm going to say, is 4 lower or is nothing? There's nothing left on the left side, then I must know that everything on the right has to be bigger than everything that's in the merged array right now. So instead of saying, OK, I'll put 4 in and then I'll put 6 in, because the only thing left is on one side, everything must go. So that all comes down. And let's again take a second and think about where we are. At this point, for the original brick red array that we started with, we have gone through 2 of our pseudocode steps. We've sorted the left half of that overall brick red array, and we sorted the right half of that overall brick red array. And so now the final thing we have to do is merge those two halves together. And just like before, we continue to ask ourselves the same question again. Which is lower, 1 or 3? Notice the little black line there dividing the two halves to make it more visually clear. Which is lower, 1 or 3? Well, 1 is. Now again, I ask myself the question, which is lower, 2 or 3? That would be 2. Which is lower, 5 or 3? That's 3. 5 or 4? It's 4. 5 or 6? 5. 6 or nothing? It's 6. And so by going through this process recursively and breaking my problem down into smaller and smaller subarrays, sorting those, merging them together, after a number of steps, I have now completed my sort, and I have everything in order here in dark blue, 1, 2, 3, 4, 5, 6. It's not necessarily as straightforward as something like bubble sort, insertion sort, or selection sort, but are there some advantages here? Well, the answer is yes, there are. In the worst case scenario, we have to split up n elements, and then we have to recombine them, effectively doubling the sorted arrays as we build them up. So we take 2 one-element arrays and we turn it into a 2-element array. We take 2 two-element arrays, we make it into a 4-element array, and so on and so on and so on as we go. In the best case scenario, sort of like selection sort, the array is already sorted, but we don't know this. We don't know this until we split it and recombine it back with this algorithm. There's no sort of shortcut here other than doing a search beforehand, but that's going to add extra time as well. So the result here is that we have n elements, and we might have to combine them if we're doubling log.
No sé por qué. Ok, entiendo. El merge sort es más eficiente cuando trabajo con arrays grandes y el sort común es cuando usa arrays pequeños. Bueno, no deja de ser un despelote porque es
much. So merge sort, where is this magical algorithm? What are we actually doing, wasting time on these other things? Well, let's consider exactly that, but we need sort of a secret ingredient. And let me revisit Mike Smith for just a moment. So you'll recall this was the pseudocode that we had for Mike Smith in week 0, and we decided when Mike is earlier in the book or when Mike is later in the book to just go to an earlier step, thereby inducing some kind of loop. But suppose we change that language to be this instead. Don't go to a specific line number. Don't go to some earlier step. But just more generally say, search for Mike in the left half of the book, or search for Mike in the right half of the book. This is borrowing an idea that I proposed a moment ago when we were searching for something else. And what word did we ascribe to this kind of approach of this cyclical use of your own definition? Yeah. Recursion. So recursion is actually this secret ingredient that we can leverage both intuitively and in code to implement this new and improved fourth algorithm, merge sort. And indeed, this we'll use as demonstrative of a class of algorithms that doesn't behave in quite the same way fundamentally as selection sort, insertion sort, and bubble sort. Indeed, you can do better than big O of n squared. You can do much better, as you felt a moment ago with that visualization. And merge sort is one such algorithm with which we can do that. And amazingly, the pseudocode is this simple. When you're given n elements, if n is less than 2, just return, right? If you have fewer than 2 elements, the list is of size 1, which is sorted, or size 0, which is also meaninglessly sorted, so you're done. So that's kind of a base case, like a default scenario. Let's just make sure that no matter what, we eventually quit, even if the list is super small. But then the magic is hidden in those last 3 lines. Else, sort the left half of the elements, then sort the right half of the elements, which is completely punting, so to speak, just kind of recursively calling yourself. But the key detail here is that then you have to merge the sorted halves. So you're not just looking for Mike to the left and looking for Mike to the right. You're doing something on the left, something on the right, sorting each half, but then you have to kind of weave things together. And we'll see how expensive that actually is. So let's take an example. And I mock this up with some very simple animation so we could walk through it step by step. But consider the following. So here's that same list from before where we had a whole bunch of volunteers. But rather than call up humans, we'll just do this visually. Let me consider the fact that this is really just an array. So I'm just going to box everything like this. And this is actually key that we have random access to these elements. We can jump right to the elements we want, and code ultimately too if we cared. And now let's focus on the left-hand side. So I've wrapped 4, 8, 6, 2. In a solid line and left everything else dashed because I want to focus our attention on sorting the left half. So again, to rewind, this is the algorithm. And the goal at hand is to walk through visually an example whereby we sort 8 elements. And we do that by sorting the left half, sorting the right half, and then somehow merging these things together. So how do we do this? Well, let's consider the left half. All right. How do I sort a list of 4 elements? What does it mean to sort the left half? Well, what algorithms do I have in my toolkit for sorting elements? Yeah, selection sort, insertion sort, bubble sort, but merge sort. And that's where this gets weird quickly. You want to use your same algorithm to sort the left-hand side of this list, and yet we haven't even finished defining this algorithm, but that's going to be OK we'll see. So let's sort the left half. How do you sort the left half of a list? Well, you sort a list of size 4. What does that mean? How do you sort a list of size 4? Sort the left half of that. So let's focus on 4 and 8. All right, how do you sort a list of size 2? Merge sort it. So how do you sort a list of size 2? Sort the left half. OK, beautifully. Done. Right? Done. Sort the right half. Nice. Done. I mean, I'm doing real work, or claiming to, but now I have to do something more. Now I have to merge the two halves. So I'm taking a step back. I have 2 lists now, one of size 1, one of size 1. I have to merge these things 2 together. Which comes first, 4 or 8? 4. So let's create some extra space for it. Let's put 4 here, and let's put 8 here. So here's a key detail with merge sort. Kind of cheating, at least at the moment. I'm using some extra space. So I hope you won't mind. To achieve this, I'm using more memory, more RAM that I wasn't allowing myself for selection sort, bubble sort, or insertion sort. OK, so now it's going to be easy to get lost quickly. So what have I just done? I have sorted a list of size 2 by sorting the left half, done, right half, done, merging it together. So now I have a sorted list of size 2. Rewind the story. What step comes next? Sort the right half that was of size 2. So if you kind of mentally buffer all of the to-dos that we're doing and then pluck them off as we go, you'll see where the story goes. Now I want to sort the right half of the original list, or sorry, the right half of the left half of the original list. How do I do that? Sort the left half, done. Sort the right half, done. Merge them together. What comes first, 6 or 2?
2.
OK, so let's give ourselves a little more memory for that. So we have a place to put it, 2, and then 6. All right, so it doesn't look like all that much progress, frankly. My left half of the list is now 4, 8, 2, 6, which is not really sorted, but we'll get there. What step comes next? I've just sorted the right half of the left half of my original list. You're missing a step. Merge, that third step. Once you've sorted the left half of something, then you've sorted the right half of something. Now you have to merge them or weave them together somehow. So the left half of the list in the story at the moment is 4 and 8. The right half is 2 and 6. So here's where you can kind of bring out your fingers to think through this sort of conceptually or in pseudocode. Here's the left list. Here's the right list, or the right half. So how do I merge these two together? Well, it turns out, and you can see it now. Before it was idiotic that we just were merging lists of size 1. It's pretty easy. Here now we have something substantive to talk about. So I have one list here, one list here. Which element from these 2 lists obviously comes first?
2.
So 2. And so what I'm going to do is then 2 is going to have to come down here. And then I can advance my right hand, so to speak, and now compare 4 and 6. What's going to come next?
4.
4. Now I can advance my left hand. I compare 8 and 6. Which comes next?
6.
6. Now my right hand, its job is done. I have only one more to do, and this. So what's key in the merging is that you essentially have this left hand and this right hand concept. Each of them kind of steps forward over time, but you never go back. You never double back. So it's this sort of linear relationship with your left and right hand as you're merging the lists together. So pictorially, let's see that. We compare 4 and 2. 2 goes first, then 4.
6.
Then 6, then 8. Where am I in the story? I mean, we've been droning on for some time now. I have just successfully sorted what? The left half of the original list, which means the next step is
The right.
sort the right half of the original list. So I can box that in to draw attention to it. How do I sort a list of size 4? Well, that's really just 2 lists of size 2. Let's sort the left half. How do I sort a list of size 2? Well, that's really just a list of 2 lists of size 1. Done. 1 is sorted. Done. 7 is sorted. Now I have to merge them together. 1 comes first, then 7. OK, now sort the right half of the original list. OK, sort the left half. Done. Right half. Done. Merge them together into some extra space. 3, and then 5. Now where am I in the story? Now I have sorted the left half of the original right half and the right half of the original right half. So now I have to merge them together. So 1,
3,
3,
5, 7.
5, 7. Almost there. Now we're sort of rewinding in time. Now we're at the very first chapter in the story. Sort left half, sort right half, merge. I have that one final merge step. So what comes first from the left half and the right half?
1,
1,
2,
2. Even if you've lost track of the story, the answer is going to be 1, 2, 3, 4, 5, 6, 7, 8. But 1, 2, 3, But notice what's happening here. In effect, whatever code is implementing this, it's as though like my right and left fingers are just moving from left to right, plucking off the element that is indeed then the smallest. Whew. That was a heck of a lot of work. And frankly, that story seemed to take longer to tell than any of the others. But what happened? And in fact, I've left deliberately with this little animation of sorts on the screen the remnants of where we came. And it looks like I really cheated, though, right? I seem to first say, hey, I need some extra RAM, and I took it. And then I didn't mention I needed more RAM. I didn't mention I needed even more RAM. So this seems to have taken like 4 times as much total memory than any of our previous algorithms. But that's not actually the case. I left this here pictorially so we could see the history. Technically, you do need more RAM to implement this algorithm, merge sort. But we could have cut corners. Instead of merging down here, we could have just merged back into our original chunk. And so we could have just bounced between 2 separate arrays. But this is just a little more clear in terms of remnants. So how many steps did this take? Well, how many times did I divide my original list in half, in half, in half, effectively? I had 8 elements here. And that was really like if you divide it up differently, 2 bigger halves and 2 bigger halves. But if you divide it again, that's like 2 really big halves. And then you get 1 big list. So it would seem that starting here, I divided it 1, 2, 3 times. I did some splitting, left half, right half, left half, right half. And anytime you split something in half and half and half and half, what's the running time of anything involving like halving again and again and again? It's like binary search. Log n, log n. So anytime you see in computer science more generally, certainly CS50 in upcoming weeks, this division and conquering again and again and again, where you're dividing something in half, odds are logarithmic running time is somehow at play. But this algorithm, merge sort, surely cannot run in big O of log n time. Because again, you can't sort n elements in less than linear time, because you'd be guessing that everything is sorted. So log n is not the final answer here, but there is something logarithmic happening. However, even though we did a left half, right half thing, a left half, right half thing, a left half, right hand thing, sort of a total of 3 times, from here to here to here to here, at which point we were done, on every row that's on the screen, if you will, what did I do with my left and right hand? I sort of always did n steps, right? Even if you can really see it up here, how did I merge this last thing? I had to touch all 8 elements by walking through the list. How did I merge these 2 left halves? Well, I had to do this, and then I had to do this. So if you kind of consider the remnants of my fingers touching the screen, every time I did a divide and conquer, I had to touch every element in order to merge them together. So I did log n things, and every time I did that, I incurred n steps of merging. So log n things times n is going to give me big O of n log n. So this was a
Ok, creo que me pasé. Estamos 14. 14.
among the options on our sort of menu of possible running times, at least that we'll focus on right now. This is bigger than log n, of course, because you're multiplying it by n. But it's smaller than n squared, because if log n is less than n, then surely n times log n is less than n. And so the running time here of merge sort is indeed going to be big O of log n. Any questions on this here? All right, if I may, let me point out one other approach for seeing this same thing as follows. You can actually glean this kind of detail more formally, especially if you're the mathy type, from the pseudocode itself. We didn't have to walk through this whole verbal exercise or visualization thereof. What if we just go back to basics and just analyze our own pseudocode or our own C code eventually, line by line? So here's the original algorithm. How many steps does this take to just check if n is less than 2, return, we're done? Big O of what? It's just 1 step, or maybe it's 2, like the if and then the return, but it's constant. It's 1 or 2, we can debate that, but it's constant. It has nothing to do with the size of n. You're just making a finite number of decisions there, 1. So you know what? The running time, which I'm going to formulaically say is t of n. So the running time.
Hi, the topic is merge sort. So, for understanding merge sort, first of all, we should know what is merging. So, let us
Creo que entendí el concepto. A ver.
now. We have seen what is merging, and also we have seen
Mm, a ver. Vamos a poner 2, 3, 1, 5, 4, 6. Acá lo divide a la mitad. Ok. Lo divide. Ajá. 2, 3, 1. Ahora va a dividir el array de la izquierda y lo divide en 2, 3, en 2 y 3 y 1 o 2, 3 y 1. Ah, ok. Lo divide en 2 y en 3. Este está ordenado. Ahora va a dividir 2 y 3. 2 y 3. Va a ser merge de este 2 y 3. 2 y 3. Como no se puede ver, va a ser merge. Como hace 2 y 3. Ahora tiene que comparar el 2 y el 3 con el 1. Ah, selecciona el mismo valor. 2. Ok. Después va a ser merge del 2 de eso. Ok, termina de hacer el merge. Un array de 1 no puede ser dividido, así que está listo para el merge. Queda en 1. El valor más chico es el 1. 1. Ahora me quedaba el 2 y el 3. Ok, 2 y el 3. Ese ya está ordenado. Está listo. Ahora hacer lo mismo. Separar 5 y 4 y 6. Va a dividir 5 y 4. Y lo va a ordenar. Ahora cuando quiera hacer el merge va a pasar el 4 a la primera posición. El 5 y hace merge. Ok, el 6 no se puede dividir. Hace merge. Va a comparar entre estos dos. El valor más chico va a ser el 4. Entre el 5 y el 6 va a ser el 5. Ok, el 6. Y ahora hace merge de las dos mitades y compara. El 1 es más chico que el 4. Sí, listo, va al 1. El 2 es más chico que el 5. Sí, va al 2. El 3 es más chico que el 5. Sí, va al 3. El 4 más 5. El 4 más 5 es más chico que el 5. Sí, va al 4. El 5. Cuando esta está vacía, empieza a copiar todos los valores que están ordenados de la segunda mitad. Ok. Ok, tiene... Está bueno para entenderlo con... Interesante. Ok, vamos a poner musiquita de nuevo. Vamos a poner por acá. Vamos a poner esto por acá. Mm, Bueno, se usa la recursividad. Tengo que usar una función recursiva. Pero yo no voy a perder tiempo con esto. No sé qué vamos a usar el buen amigo del chat GPT. Le voy a pasar esto. Okay, vamos a ver en JavaScript. Hacer un feed nuevo como Bootcamps, sort 3, 1, 2, 5, 4. Ok. Bueno, esto es lo de que se ve en el curso de CS50 de Harvard. Okay, voy anotando. Esto lo tiene FreeCodeCamp, me parece, en la parte del proyecto de Euler. Pero acá está. Bueno. Tengo que hacer el... Ok. Vamos a copiarlo y ahí cambio la escena un toque. Estoy armando el repo. Te muestro lo que estoy haciendo. Estoy usando el cliente de escritorio de cosas. De GitHub Desktop o algo así se llama. Vamos a abrirlo. pero no me acuerdo cómo era para ejecutarlo. A ver. Ah, con Node. Okay. Node index. No. Node menos C. Node menos C. ¿Cómo se llama esto? Bueno, no importa. Sé que funciona porque está probado en el FIP. Okay, esto está. Vamos a crear un readme. Vamos a darle crédito a ChatGPT porque vamos a poner un git status git branch git add git commit add Vamos a hacer un git push. Ok, acá lo pushamos. Y me vamos a ir a GitHub. Ok, bienvenido. Bien, acá lo subimos. Vamos a ver la resolución. Ok. Bien, si me voy a ver el código, me llevo al GitHub. Está todo el código. Pedimos crédito. Que hoy son 30 de junio. Hola Matías, ¿cómo estás? Odin Project está buenísimo. La verdad que, o sea, si sabes inglés, lo podés hacer perfectamente. No es como Bootcamps que te va llevando de la mano con el navegador. Esto te obliga a instalar Linux, el editor de código. Bueno, escribir código en el editor. Usar mucho Git. Hay muchos recursos. En español te recomendaría quizás Open Bootcamp. Sí, Open Bootcamp. Tiene buen material. Bueno, es 30. Bien, vamos bien. Ok, esto está. Vamos a dar complete. Complexity, esto no sé qué es. Tiene- Eso está bueno también complementarlo con Full Stack Open. Pero bueno, ya cuando tenés más experiencia, porque no es para. Lo probé yo y la verdad que me di contra una pared. Ok, esto lo vamos a cerrar. Bueno, time complexity. Bueno, voy a ver por dónde vamos con la currícula. A ver. A ver. Space, Command Data Structure, Algorithm. Listas enlazadas. Búsqueda de árbol binario. Y esto no sé, caballeros, no sé qué. Ah, esto es el ajedrez. Después viene el testing. Git. JavaScript en backend. Bueno, antes de pasar acá, vamos a hacer todo esto. A ver esto. space. ¿Qué otra cosa?
Started as a whisper, message from a new world I'd never.
Bueno, lo voy a dejar por acá. Y después de la tarde voy a seguir con esto. Voy a tratar de leer todo esto. Time complexity. Tiempo complejo, que así es la traducción. Sí, voy a hacer eso. Así que bueno, gracias a los que pasaron, comentaron. Y nos vemos después de la tarde. Saludos.